All right, so this is a constant acceleration lecture here. And if we already went over some of this in class, feel free to fast forward through it. But otherwise, make sure you're writing all this down. So we're going to start by going over constant acceleration formulas, also known as K formulas, also known as kinematics formulas. So I'm just going to add this to the top. So these formulas only apply to situations where the acceleration is constant. And when is that, or why worry about that? Because sometimes the acceleration is only constant, right? It is always constant, and then that would be when objects are in free fall, right? So let me close this back up. So for instance, around the planet Earth, anytime an object is falling, we know that its acceleration points straight down towards the center of the Earth. And because there's a force of gravity. If the object is on that side of the Earth, it would point straight down. If the object is on the bottom of the Earth, it would point straight down. It always points towards the center of the Earth. And this value of these vectors, or these arrows I'm drawing, is G. So, it's 9.81. And we like to call 9.81 baby G. So I'm saying that this magnitude, this amount of this acceleration, 9.81 meters per second, right, is equal, right, this is 9.81 meters per second every 1 second, right, is equal to 9.81 meters per second squared. It's the same thing, which is equal to baby G. All right, and that's how that's how much this comes up, right? That we give it its own variable, baby G, and baby G is the Earth's gravitational field. So if you go to a different planet, the baby G is different. For instance, I think on the moon, right off the top of my head, I think it's around 1.6 meters per second squared. We'll say approximately, in case you're wondering. The moon doesn't have as much mass as the Earth. Its gravitational field is smaller. So anywhere around the Earth, you have this gravitational field. You have this force field. You have this acceleration that this force field causes. And the further you get away from Earth, the smaller that acceleration gets, right? When you're near Earth, it is always trying to draw these towards the center. Not very well. It is always equal to 9.81. But if you were in a plane flying over the Earth, it would be a little weaker. Now, not much weaker. You can be, a few miles up in the air, and it's not going to be much difference on baby G. And I forget how far up into the air you have to be, or into the Earth's atmosphere, or outside of the Earth's atmosphere, before baby G significantly decreases. So I shouldn't just say a few miles. I'm not positive on what it is. But eventually I'm saying that this vector would get smaller and smaller still. And so the further you are away from Earth, the smaller its gravitational field is on you, right? The smaller that acceleration gets. But anyone near the surface of the Earth, in a tall building, on a plane, is going to experience 9.81. Unless they go out of their way to go so far away from the Earth's surface that they want to decrease 9.81. So Anyways, so this is what we're dealing with here. And this is a acceleration 9.81 that is constant, right? And so any object that's falling, right, if I drop a tennis ball, it's in free fall, and it's just going to fall, it's going to accelerate towards the ground at 9.81. Now, because we like to call down negative, it's pretty common in this class that baby G gets a negative sign, right? This is equal to negative G. And what I want to state here, though, is G is not inherently negative, right? It is positive. And G is a magnitude, it's amount. It's directed towards the center. So you apply the sign with direction, right? So I'm saying, right, for instance, here, down is towards the center of the earth, but here, down is towards the center of the earth as well. And so based on where you are on the earth, down is relative, right? Because if you're on top of the earth versus on the bottom of the earth, down is going to be a different direction. But we like to refer to down as being negative and not worry about that. But I just want to once again reiterate that G itself is not negative. G is positive. You make it negative if down is negative. So G is negative when down is negative. That's what I'm trying to say. I'll write that down. G is negative. So I mean 9.81, right? Meters per second squared is negative when down is negative. All right. If down was positive, G would be positive. And then that's all there is to it there. Okay. So let's go ahead and talk about these constant acceleration formulas, which will apply to objects in free fall, right? A falling tennis ball, a football you throw up in the air. Anything that is only under the effect of baby G or only under the effect of the force of gravity or the Earth's gravitational field is considered a projectile. So projectiles utilize this motion here, right? These constant acceleration formulas. So what we're saying is the variables, and I'll go ahead and write them out here. These variables, let's go ahead and jot these down. VI is initial velocity. What I was trying to say is these variables have a relationship based on some mathematics, based on calculus, that they relate to each other in a certain way when the acceleration is constant. So when you have any situation with a constant acceleration, it doesn't have to be a falling object. It could be any situation. Maybe you're in your car and you're constantly accelerating in your car at 1 mile per hour per second, right? Every second you increase your speed by 1 mile per hour. Then these variables right here that I'm writing out, there's going to be 5 of them, are going to have they're going to have certain mathematical relationships every time. Make sure you spell acceleration right. 2 C's, 1 L. What do we forget? Delta X or displacement. And you might need a separate sheet of paper. You can see I'm going to go ahead and get another sheet of paper because I like to write large and I want space, right? Okay, so I have these 5 variables that are going to be mathematically related in these formulas called K formulas. Now there's technically 5 K formulas. All right, if we look up here, we see spots for 3. On the AP test, you get 3. I'm going to give you 4. I honestly don't know what K5 is. I'm sure I've looked it up before. I may even look it up in class, or actually make a poster of it, just because I'm kind of curious what it is. But we'll go ahead and write 4. Like I said, 3 on the AP test, 1 that I think you should memorize, even because it's useful. And we'll talk about why. Now you might say, well, why is there so many dang formulas, right? And the answer is because the formulas address what you don't know. And so let's write these down and then I'll come back to that. So I like to call the formulas, instead of constant acceleration formulas, I call them K formulas. The K stands for kinematics. Kinematics is what we've been doing for the last couple weeks. Kinematics in one direction, right? 1D, one dimension. So kinematics is the study of motion. Pretty obviously, right? But not only that, it's the study of motion without regard to how the object started moving. Right? We never talked about, what caused the object to move. All right, so we have these formulas called K formulas. So we'll go ahead and talk about the first one, K1. But before I just write it out, right, because I could, I'm going to actually write out this formula instead. Okay, so you should recognize this formula. It's our acceleration formula. I'm going to write it without the delta on the t. I like to disregard that delta. How can I do that? Because I think the initial time would be 0, and you don't have to worry about it. If that doesn't make sense, just don't worry about it and just go with it. A lot of times I drop the delta off the t. All right, it's that simple. Okay, A equals delta V over t. All right, so here we have this formula. Let's go ahead and expand it out. All right, let's go ahead and rearrange it. Let's solve for VF. So I'm going to go ahead and multiply both sides by t. Cancel here. I'm going to rewrite. So I have AT equals VF minus VI. I'm going to go ahead and kick the VI over to the other side. I'll just do that by adding VI to both sides. Canceling once again. I guess I probably should have wrote this in red. Dang it, what just happened? Adding VI to both sides. Notice now why I make my T's with curls, right? I make my T's with that curl at the bottom because that way they don't look like plus signs. And now you can start to understand that a little bit better with these formulas. And if you can't see it yet, you will see it in a second. All right, so negative VI cancels positive VI. Now I'm going to go ahead and rewrite. So I'm going to actually write it with the VF over on this side. So let's do a little switcheroo there on my equation. Equalities, it doesn't matter which side you write first because both sides are equal. So VF equals VI plus AT. So this is a rearranged form. Let me get my highlighter. This right here, yellow, this right here is a rearranged form of the equation you already knew, your acceleration equation right here. All right, and this is K1. Okay, so let's go ahead and add that to our list up above, what K1 is. Once again, these formulas aren't always true. They're always true, though, when something accelerates constantly. When you have an acceleration that is just a number that stays the same. But they're not always inherently true, right? Maybe your acceleration is changing. Maybe you're driving down the road and you decide to accelerate at 1 mile per hour every second, but then you decide to get after it and you're going to go 2 miles per hour every second. And then you slow down because you realize you started speeding and you decrease your acceleration by 3 miles per hour every second. So you can see that's a changing acceleration. It's not constant the entire time, so you couldn't use these formulas over that entire time. So you could use them for chunks of time, right? Like, for instance, when you're driving and speeding up by 1 mile per hour per second. And yeah, you could use it for a chunk of the motion. All right, so anyways, let's go ahead and get back to this. The next equation is going to come from doing an integral. It's going to come from calculus. And anyways, we're not going to worry about that. We're just going to go ahead and use it and memorize it, and that'll be just fine. It works just as well whether or not you know calculus or not. It's perfectly fine. So let's go ahead and write that out. I also curl my eyes. I really don't have a reason for that. I just like to do it. Now, only the t is getting squared there. Only the t is getting squared. All right. The parentheses, do they have to be there in that certain way? Probably not. I write them sometimes without the parentheses. I'm just trying to make it visually make sense. All right. So, but only the t is getting squared. So that formula reads delta x equals VIT plus 1/2 AT squared. Okay. Good. K3. All right. And K4. Now, will you have to memorize these? No. Ideally, you would use them so much that you would memorize them just because you use them so much. But I will give these to you on tests going forward. I think one year I did do a quiz where you had to memorize them. I thought that was kind of cool. And the kids liked it. I mean, I don't know. But ideally, the best way to learn it is to actually use the formulas and memorize the formulas by using them. All right, so those are our 4 kinematics formulas. Let's now, what do we want to do? Do we want to talk about, let's talk about first, before we use them, let's talk about why there are so many, right? You might say, well, what the heck? Why do we need all these formulas? And that's a great question, right? So the reason is, like I said earlier, is what you don't know. So meaning each formula is used based on not what you know, well, kind of what you know, but it's mainly based on what you don't know. So you pick the formula. Most students will always pick the formula they need based on what they know. But what I want you to realize is the formulas are different based on what you don't know. So for instance, in the first formula, something is missing in K1, right? And if we look at just K1, one of these variables right here, right, VI, VFT, or A, or delta X is missing. And which one is it? Which one's missing in K1? This is K1 right here, right? You would say delta X. So each formula is going to have something unique to it that's missing, is what I'm trying to say. So if we come back to the next one in K2, what's missing in K2? Once again, one of the 5, VF. All right. And this is not part of the formula, right? We're just pointing out why we use the different formulas. So we use K2 when we don't know VF. What about K3? I like this one. This one shows up is pretty important because sometimes you don't know this and it's pretty useful. So you don't know time, right? Yeah, so when you don't know time, K3 is the formula you want to use. And finally, K4, acceleration. So I don't know what K5 is, right? But I do know that it's the formula that is going to be missing what variable? Well, you should say the only one that's left, which is VI. All right. And kind of want to look that up and write that down. But I'll save that, and maybe like I said, I'll make a poster of it in class or something. K5. I don't think I've ever used it, maybe once. And I know it's in my Cutnell and Johnson physics book over there. I just got to get up and open the book and find it. But yeah, we'll talk about it in class if you're interested. If you don't care, then just fine. You're fine with 3 formulas, and I gave you 4. You don't really need K5, okay? You can derive K5 and K4, I want to say, from the first 3, but I'm going to go ahead and give you 3 or 4 on the test. AP test only gives you the first 3, doesn't give you the 4th one. Okay, so now we have some example problems that we're going to look at here. So let's do some examples now, going over some constant acceleration formulas. And you have this page here, 13, 14, and 15. When you do these problems, looks like there's 4 parts over here. You can kind of ignore that. You don't have to worry about A, B, C, and D. Just solve the question, and I'll kind of show you how, and you can just do it in the same way that I do right now. So when I read a problem, I like to kind of underline or highlight what's important. I'm going to do problem 15, and then I gather up my variables at the bottom and then pick an equation to use. So this problem says a moose runs for 6 seconds. It accelerates at 1 meter per second squared after having an initial velocity of 3 meters per second. How fast is the moose going after 6 seconds? So I'm going to go ahead and kind of highlight what I'm seeing here. So the first thing is 6 seconds. This is the time. Accelerates at 1 meter per second squared. There's our acceleration. Initial velocity of 3 meters per second. That's VI. How fast is the moose going after 6 seconds? This is asking for what's happening to its velocity, how fast, and after 6 seconds. So this is at a later time. So that means we're looking for a VF, right? So what we're doing then here, and I'll just go ahead and gather those variables up. I like to just write them all out. T equals 6 seconds. A equals 1 meter per second squared, or 1 meter per second, and VI is equal to 3 meters per second. All right, good. And then we want to know VF. So we want a K formula that doesn't have anything to do with delta X, but will get us VF. So it shouldn't have delta X in it. Let's go up and look. Which formula does not have delta X? And that would be K1. So K1 is going to allow us to find VF and using VI and AT. So we're going to go ahead and come back down here, write K1 out. Always write it out. This is how I memorize my formulas, is that I'm always writing them out. There's no real trick to it, just repetition, and eventually you'll remember them. VF we don't know, so I'm just going to rewrite that. VI is equal to 3 meters per second. The acceleration is 1 meter per second squared, and we're multiplying that by our time of 6 seconds. This is over 1, by the way. All right, so I'm going to then grab the red marker here, cancel off one of these seconds with this second on top, and that's going to give me meters per second over there. So switch back to blue. So we're saying that VF then is equal to 3 meters per second plus 1 meter per second times 6, which is just 6 meters per second. And that's going to give us 9 meters per second. All right, so this is our answer for VF here, right? Is 9 meters per second. All right, and that is VF. Okay, so then there's kind of a bonus question at the bottom, and it says, how far does the moose run? All right, when it asks for that, now it's asking about that last variable that we kind of didn't worry about, right? Meaning, what is delta X? We just said that VF, right, is equal to 9 meters per second. But now we need a K formula that has delta X in it. So I'm going to go back up to my formulas, pick one that has delta x in it. I see 3 of them, right? All K2, K3, and K4. So which one's the right one to take, right? And the beauty of it is that they all should work. Now, K2 is obviously very convenient, meaning that delta x is on the left. It's already there to be solved for, so I think most students would pick K2. But I'm going to be difficult here, right? And I'm going to pick, I'm going to use all 3 of them, right? And maybe I'll use the tougher ones first. So let's go ahead and start with K3. I think K3 is the least likely one that a student would pick. All right, let's go ahead and plug in what we know, and we'll just bring the numbers down from up above, right? We see that VF is equal to 9 meters per second, but we have to square it. VI is equal to 3 meters per second. That also gets squared. Plus 2 times the acceleration, which is 1 meter per second squared, times our delta x, which we want to know, right? We got to have one thing in there that's the unknown, because that is the variable that we're solving for in the equation. All right, so I'm going to go ahead and square the 9, square the 3. Notice the units square with it, right? The meters square, the seconds square, and that's important. Okay, so we're getting something like that. We'll subtract 9 from both sides, and these units go with it. So minus 9 meters squared over seconds squared, minus 9 meters squared over seconds squared. I usually write that differently, but that's okay. I don't mind writing it this way. I think students like it when I write it like that. All right, so I cancel both of those, and I'm left with 72 is equal to 2 meters per second squared times delta x. And now I can just divide both sides by 2 meters per second squared. So we have a fraction in the bottom of the fraction, and I think I'm going to have to show you what that looks like. I could do it for this side, but I'm not going to worry about it. I'm just going to do that, and I think everyone's going to be okay with that. I think this side is where everyone is not going to be okay with me just going quickly through this. So when you have a fraction, right, here's my fraction I'm talking about, right, hanging out in the denominator. We have to do something called multiplying by the reciprocal. What's the reciprocal of 2 meters over seconds squared? It's the flip of it, right? The reciprocal would be, where can I write this? I have a little space here. The reciprocal, well, I'll just write it right here. I'll write it right underneath. Is going to equal seconds squared over 2 meters. So when we divide by a fraction, we multiply by its reciprocal. So we're going to multiply 72 meters squared per second squared by this reciprocal, right? By this. And that is going to be our delta x. So what happens there, right? Well, let's look at it, right? This is just one giant fraction, right? So our seconds squared can cancel. Our meters on bottom can cancel one of the meters on top, but we're still left with a meter on top, which is good because delta x is in units of meters. And then we have a 72, right? Don't forget the 72 divided by 2. So what's 72 over 2? 36. All right. So we can see using K3 that we get delta x equals 36 meters. All right, let's be difficult one more time and use K4. I don't know if I have room. I'm going to have to add a sheet of paper here. Let's see. All right, so let's so K3 this time? No, we just did K3, K4. Okay. So we're saying K4. Delta x. I guess this one has delta x over it, all the way over on the side. I don't know why I didn't say that earlier. It's just delta, or K2 is just what I'm used to. So K4 delta x equals 1/2 VF plus VI times T. Delta x then is going to equal 1/2. What was final velocity? It was 9? Yeah. And, whoops, I don't want to put that there. Okay. 9 plus, I think initial was 3. And our time was 6 seconds, I believe. All right, so we're saying then delta x is equal to 1/2 times 12 times 6. Notice that's over 1. So notice what I'm trying to show you here, right? I'm showing you that these seconds are going to cancel. We're going to be left with meters like we expect. We have 12 times 6 on top, which is 72, divided by 2, right? So this is once again going to equal 36 meters. So it didn't matter. K3 or K4 will get us to the right answer, right? This is K3. What about K2, which is the one I think most students would have taken? I think K4 might have actually been the easiest, though. So maybe students would have picked that. I don't know. You know what you would have chose. All right, so delta x is equal to VI, which we said is 3, times 6 seconds over 1, plus 1/2. I think the acceleration was 1 meter per second squared. Time was 6 seconds squared. And I'm going to grab that red pen. Whoops, or the eraser, my fault. The red pen. This was 3 meters per second. I don't know why I'm struggling to write that. And we're going to cancel our seconds and be left with 18 meters. Plus, over here, we're going to cancel, well, let's finish multiplying here, right? 1/2 times 1 meter per second squared times 36 seconds squared over 1. All right, so now you can see what cancels for unit. Seconds squared cancels seconds squared. Whoops, what did I just do? Go away. All right, so this is going to be half of 36, which is 18 meters again. All right. Okay, you get the idea. All right, so it doesn't matter which formula you take. They all work the same. All right, good. I'm going to go ahead and pause it there, and we'll do a couple more examples in a second. So I want to do a couple examples. I know we did a few already, but from this part of the note guide here. So starting off, we'll just answer a couple questions before I dig into the examples. If an object is dropped, what does that tell us about its initial velocity? We know that means its initial velocity is 0 meters per second. We also like to call this starting from rest. If something's at rest, it has a velocity of 0 meters per second. All objects accelerate, or we could say fall, right, towards the earth at the same rate if we ignore air resistance. So they did an interesting experiment on the moon where they took a hammer and a feather, right, and pretty much dropped the hammer and the feather from the same point. And most people would think, oh, well, the hammer hits the ground first, the feather just kind of, goes back and forth and gradually hits the ground. But no, they fall at the same rate. They accelerate towards the ground at the same rate when air resistance isn't there. So this kind of blows our mind a little bit because, we see a piece of paper fall and it takes forever to fall. But if air wasn't there, then they would both hit the ground at the same time. The piece of paper and, say, a bowling ball would fall through the air and accelerate at the same rate. Anyways, I can show you that experiment sometime in class if you like. Let's go ahead and go to the next one. G stands for the acceleration due to gravity. We'll say the acceleration on Earth due to gravity. It is not gravity itself. Gravity is a force. We haven't learned about forces, but the formula, Newton's second law, is F equals ma. Forces are based off of accelerations, but a force and an acceleration are different, right? And so this is the acceleration due to the force of gravity is G. We also can call it the Earth's gravitational field. All right. Sorry if that's hard to read. I'll try and zoom in a little bit. And its value on Earth is 9.81. And remember, we said this does not have a sign, right? It is 9.81 meters per second per second. It has a sign of negative if down is negative. So I know I talked about this a little bit in class, but I want to go over it one more time. When I write 9.81 meters per second squared, I'm really saying 9.81 meters per second every second. So if an object falls, and we create a data table for that falling time period, we can go ahead and put t in seconds over here. We can put velocity in meters per second over here. And we can say at 0, we're dropping an object, so its initial velocity is 0. At time 1 second, the object will be traveling after 1 second has elapsed. After. It will be traveling at 9.81 meters per second. And the object is going to speed up by 9.81 meters per second after each second. So after I see. After 2 seconds, then we're going to tack on another 9.81 meters per second. So that would be about 19.62 meters per second. And then after another second goes by, after 3 seconds, the object would then, we tack on another 9.81. So I think we're going to get around 29.43. I don't know, something like that. And it's roughly 10 more, right? I could really just add 10 more. So if I did one more, and I add roughly 10, it's going to be approximately 39 meters per second. All right. So the problem that a lot of times students have with this is they don't know what meters per second is, or it's hard to interpret, right? Because, we travel in miles per hour. We don't really mess with meters per second too much. So I like the old shortcut of, if you have an amount of meters per second, for instance, 43, you double it. So if you double that, that's times 2 is 86. And then you add a little bit, maybe gets you to about 95. It turns out 43 meters per second is approximately 100 miles per hour. So this idea of doubling 43 to get 86, adding 9 to get 95 is not not too far off. So it's not a bad thing to do to if you're if you need a shortcut there, right? Okay, so let's go ahead and talk about, well, how can we make this more realistic to us, right? Because we don't like dealing with meters per second. So what we can say then is, while g is 9.81 meters per second, in feet per second, g is 32 feet per second. So this means that an object, as it falls through the air, will speed up by 32 feet per second every second. So once again, we can do this velocity, but this time, in feet per second. And if we do that, we can go ahead and say, well, it starts at 0. After 1 second, it's going to be going 32 feet per second. After 2 seconds, it's going to be going 64 feet per second. After 3 seconds, it'll be going, let's add on another 32, so 96. After 4 seconds, 128. Now, obviously, air resistance, if it's there, is going to have something to say about this. It turns out when you double your velocity, you quadruple your air resistance. So that catches up, and we hit something called terminal velocity. So if you were to drop a penny off of a really tall building, right, it wouldn't speed up forever. So that is true of all objects as they travel through the air, right? That the air is going to slow them down because of air resistance. And at some point, it'll just hit a max speed where it'll stay. So if you go skydiving, the max speed for a human is around 120 miles per hour. So, all right. Anyways, so that's the idea behind acceleration. And now you can kind of see 9.81 is about 32 feet per second. So you're going to speed up really fast. For any falling object, is going to speed up really fast. Okay, let's take a look at number 4 here. An orange is dropped from a building. It falls for 12 seconds. How tall is the building? All right, for this problem, I really like to draw these problems out. So down here, I'm going to go ahead and draw this building. Oops. All right, so we got a building here, and we're going to drop an orange from the top of it. Okay, so when the orange falls, it's going to travel the height of the building because it's being dropped from the top. However, h isn't one of the variables we like to work with. And furthermore, it's not really about the building. It's all about the orange. The orange is going to undergo a displacement in this problem. And it's going to be in the vertical direction. So that means the y direction, right? So I like to call downward in the y direction the negative direction, and upward in the y direction the positive direction. So I'm saying that positive y will point up and negative y will point down. Okay, so if you really want, you can call down positive if you like. It doesn't have to be negative. All right, so what else do we know? Question 4 says it falls for 12 seconds and then asks us how tall is the building. So really they don't give us a lot. They just say we're going to drop an orange. It's going to fall for 12 seconds. How tall is the building? So there's got to be some hidden information there in order to solve this problem, right? To use a K formula, and there is. So because the orange is dropped, we know that its initial velocity is rest, or 0, right? It's going to start at 0 meters per second. Because the orange is dropped also on the planet Earth, we know that what its acceleration is. Its acceleration is going to equal g, which actually it's going to be negative g, right? Because it's pointed downwards. So that means the acceleration is going to equal negative 9.81 meters per second squared. We know that the orange is going to displace some amount delta y, but we don't know what that is. So that's what we're going to solve for, because we know delta y is going to be related to the height of the building, right? They'll be similar. And I think we know time, right? It falls for 12 seconds. Okay, so I'm going to write that down too. And this is what I always like to do with these problems, just gather up my variables, draw a diagram, gather up my variables. It's just an easy way to solve physics problems. All right, so now we need a K formula that's going to give us delta y, right? Because we think when we have delta y, how the displacement of the orange, we should be able to say what the height of the building is. So I'm going to go ahead and write K2 down. Delta y equals VIT plus 1/2 AT squared. And remember, this is where you like to write these formulas out so you memorize them. Let's go ahead and plug in what we know. We know the initial velocity of the orange is 0. The time it's in the air is 12 seconds. So I definitely think the orange would hit terminal velocity in 12 seconds, but it's these problems are simplified versions of what actually happens, so we don't worry about air resistance. We don't worry about terminal velocity. So we're just going to assume the orange is just going to speed up as long as it's in the air. It's going to keep speeding up. All right. Acceleration is going to be negative 9.81. And our time is 12 seconds, so we're going to go ahead and square that. All right, so I'm going to get the red marker out, cancel off this term right here, right? 0 times 12 is just 0. So we're going to be left with delta y is going to equal 1/2 negative 9.81. Notice I'm writing the units. It really does help if you follow your units and watch what they do, because you can use it to error check as you go. If your units are wrong, you probably did something wrong. So we can see here, right, that the 12 gets squared, but so does the seconds next to the 12. So we end up with 144 seconds squared. That's important because now the seconds squared can cancel the seconds squared, and that's why. Half of, let's simplify this a little more, half of negative 9.81 is negative 4.905. We can go multiply, that's going to be meters. Then we got to multiply that by 144. And I can't do this in my head. I can, probably take a guess at it, but I can't do that math in my head. So I'm going to get my calculator here. If we do the math here, I think we see that it's equal to negative 706.32. So let's go ahead and write that down. Units are going to be meters. All right, and what does that really mean, right? That is the change in y position of the orange. It is not the height of the building, right? The height of the building isn't going to be negative, but we can use that to say what the height of the building is, right? But before we do that, let's talk about why that's negative. Let's think about this. The initial position of the orange is going to be yi, which is that 706.32 meters. Though YF is going to be 0 meters. Now, something else I just want to point out before I forget is that we don't know the final velocity. And I'm going to come back to that in a second. Some of you might be saying, well, the orange is going to go splat. It's 0. It's not 0. And I'm going to point that out here in a second. Anyways, coming back to the problem here. So we have this initial y position that's positive, final y position that's 0. And so what I'm saying is now we can see why delta y is going to be negative, because remember our formula for displacement, right? I don't care that it's y. It's still going to be the same as the x formula. Delta y is equal to yf minus yi. So if I plug in those values, yf is 0. And the initial position was that positive 706.32. But now you can see 0 minus 706.32 is just going to equal negative 706.32 meters. And this is why the displacement was negative, right? That the orange is moving in the negative direction is what we're saying here. Whoops. Yeah, and so that's what we have. So the height of the building, what's that? Well, it's just going to be the absolute value of that, right? So the height of the building is going to be 706.32 meters. Now there is, and that's our answer for that part of the first part of the question. There is another part to the question, right? Which gets at the final velocity. It says, how fast is the orange moving when it hits the ground? All right, so this is for question 4, right? And I'll just put a number 4 up here. So how fast is the orange moving when it hits the ground? So what is VF, right? Well, whenever I get a VF question, I always go for K1. K1 is just the simplest formula. And and it already has VF alone, so it's very simple to use, right? So let's go ahead and solve for this VF. Now you might say, like I said a second ago, that the VF is just 0, right? And before I solve it, let me just point this out. What we're saying with the orange is that its final velocity is going to be right before it hits the ground. So this orange is cruising at its max velocity. Its velocity is going to be in blue here. It's this downward blue vector, and this is going to be VF that we don't know. But we can say for a fact it is going to be negative. It is going to point downwards, because down is negative. And I wanted to point that out because so the problem ends right before the impact. It ends the split second right before. It does not end after impact. And that's tricky, right? That's just one of those things about physics that you only know because if you've taken a physics class, right? Otherwise, you're like, oh yeah, the orange, the problem is done when the orange goes splat on the ground. No, instead we get to call the final velocity right before impact, and that's actually way more advantageous than the opposite, than saying after a collision happens, because a collision is going to change things. Collision is going to invite another force, right? The force of the ground. We want to keep our formulas, our constant acceleration formulas, constant acceleration. So let's keep them where gravity is the only force and the acceleration is only 9.81 meters per second squared towards the center of the Earth. All right, so anyways, coming back to this then, VF equals VI. VI is 0. Whoops, I'm still in blue. Dang. Let me erase that. VI is 0. Acceleration is negative 9.81 meters per second squared. And the time here is going to be, what was that, 12 seconds, 6 seconds? I can't remember, 12 seconds. All right. So, and we're going to square that, or not squaring that, sorry, we squared that above. Okay, so just 12 times 9.81. So this is going to be about 120, right? And so this is where I'm going to need to use my calculator because I am using 9.81 and not 10. So we can say that VF is equal to a negative 117.72. Now, what are the units on that? Let's look at that, right? So we got a seconds over here on top. That's going to cancel one of these seconds on bottom. And don't forget that, right? This 12 seconds is over 1. So that's why I'm able to cancel. Top and bottom are the same there. So I get meters per second as my units here. And so I do not think for an instant the orange would actually be moving this fast, right? The air resistance would have already hit terminal velocity, right? Otherwise, we have an orange that's moving at what, like 250 miles an hour or something. So I don't think that that's the case. So anyways, what would the terminal velocity of an orange be if I had to guess? I don't know. 70 miles an hour? I don't know. I'm just guessing. I would probably need an air resistance equation to calculate the terminal velocity of an orange. All right. So anyways, good. We're done with that problem. So that's it for problem 4. Let's see. Let's go back up here and look and see if there's any. Looks like the next problem is very similar, except the orange is falling for 10 seconds. The next problem, the orange is falling for 25 seconds. A little bit of repetition there. Cantaloupe in problem 7. And it's pretty much, I'm more looking at what it's asking about it, and I think it's asking pretty much the same thing. Okay, number 8's interesting. Should I just leave that for you? Let me at least help you get started on number 8. All right, so number 8 says something like this. Let me put a line through this. Okay, so number 8 says, a man steps off of a 10-meter diving board. How long does it take him to reach the water? Okay, so we're saying, let's draw a diving board. Okay, so we got a person here. Is about to attempt a dive off of a 10-meter high board. Okay, you get the idea, right? Let's draw some water. Okay, so it's 10 meters to the water. And it's going to be just like it was before. It's going to be this is going to be the change in the y position of the person. So we're saying that delta y is going to be 10 meters. But we're going to call down negative, right? So let's call that a negative 10 meters. It says steps off the board. So this means that the person is not really diving, right? And in fact, why is that important? Because that tells us the initial velocity. When the person steps off the board, what's the initial velocity? Well, it's just like the orange being dropped. It's very similar. So our VI is going to equal 0. VF we don't know. In fact, is that what it's asking us? No, it's asking us to find out how long does it take him to reach the water. So how long does it take? That's going to be time. But we do know the person is a projectile, right? They're on planet Earth. They're falling at and accelerating in the Earth's gravitational field. So the acceleration is going to equal 9.81. But since down is negative, we're going to have to call that negative. So negative baby g, or negative 9.81. All right, I don't think we know anything else, right? I don't think we know VF. So what formula do we want here when we don't know VF? Boy, we can probably go back up and look somewhere up here. When we don't know VF, looks like K2, right? All right, so if we use K2 here, just go ahead and write it in. Whoops, I'm starting by writing VF. That's wrong. We want delta y again is equal to VIT plus 1/2 AT squared. All right, and but we want to know time. Ooh. Yeah, that's actually going to be okay. Sometimes I when I get the K2 formula out, I worry a little bit because I'm like, oh man, quadratic formula time. But we're not going to have to worry about that. Why is that? Because the VI is 0. So when that's 0, that means this whole term is going to become 0. And K2 simplifies into this. Now you are going to have to square root at the end, right? And that's fine. The funny thing is, and I guess this is interesting if you've seen this before in the lab, is if we move variables around, right? And just you might recognize this from the reaction time lab, right? Multiply both sides by 2. So we kicked that half out of there and got a 2 now on the other side. Square the t. Divide both sides by a. But we do know something about a. It's equal to g, right? So I'm going to go ahead and replace that here in a second. So we can then say that, kind of running out of room, we can say that, I'm going to write it over here. We can say t squared is equal to 2 delta y over a. We know that a is g because it's a falling object. So we can say t squared equals 2 delta y over g. Square root both sides. Now you might say, well, you know what? This problem's a lot easier, Mr. Rodriguez, if you just put numbers in right away. And you'd be right. But it's sometimes cool and beneficial to solve in terms of the other variables. So you get an expression at the end that looks like this. Let me get the highlighter. You get an expression that looks like this. And this is what t is equal to, right? T is equal to the square root of 2 delta y over g. Now, we never square root negative numbers, so if you're going to make g negative 9.81, make sure you make your delta y negative as well. And so if you ever catch yourself square rooting a negative number, you're doing it wrong, and make sure you figure out why. Okay, so you can use that formula to solve for the time in the air, and but if you didn't like that derivation and you just want to, plug in numbers as soon as you can, I get it. That's the way I was as a college student when I was taking physics. I remember I was like, I don't want to move variables around. I just want to solve the problem. And so, yeah, I totally get that. All right. So I'll let you finish up some of the ones that I didn't do. I'll probably specify that on Schoology, which ones you should do for practice after these notes. And that's it. All right. Have a good day.